Okay, in this lecture, we are going to begin the topic of convection. And the topic of convection is very closely related to fluid mechanics because there is fluid flow. And when we say convection, we previously discussed this, that there is advection, and along with advection, there is also diffusion. For example, if we take a heated plate, let's say its surface temperature Ts is greater than T infinity, okay, where T infinity is temperature of the fluid that is coming and flowing over it. Then if you consider a fluid particle, okay, this particle is advected because of flow, so that is advection. And along with advection, there is also random molecular motion. So the molecules in the particle, they are interacting with molecules that are outside. Okay, so that is the diffusion part. So there is diffusion, which is due to the random molecular motion, and there is advection, which is due to the bulk motion. Okay, so that is convection. And in the problems that we did so far, actually H was given, so we did not have to determine H. Okay. But now what we are going to discuss is, we'll discuss how to determine H, but before that we'll also discuss a little bit about the physical mechanism for convection. Okay, now when we say physical mechanism for convection, the most important thing is to recognize the importance of boundary layer. So first we'll talk about that. Importance of boundary layer. And you're familiar with this idea from fluid mechanics. So again, if we consider, let's say, a flat plate and fluid flows over it, say its free stream velocity is u infinity and it is uniform. Then when the fluid comes in contact with the plate, there is going to be deceleration. Okay. The fluid particles which come in contact with the plate, they will come to rest immediately, and the effect is going to propagate. So at any point, let's say at this point, if you draw the velocity profile, it will look like this. So fluid particle is at rest here, and then velocity increases, and then you get a free stream velocity. And this is the region, say up to this point, which we call as boundary layer, delta. So this delta is, we call it velocity or hydrodynamic boundary layer thickness. Okay. And it grows in the direction of flow. So at this point, okay, delta is 0, and then it grows. So this is how, delta looks like. That is hydrodynamic boundary layer thickness. Okay. And the idea of boundary layer, we know from fluid mechanics that this is applicable when Reynolds number is high. So when Reynolds number is high, we are going to talk about this in detail later on. Then the boundary layer approximation is valid. This topic again we are going to discuss later on. Okay. But the importance of boundary layer from fluid mechanics point of view is the shear stress at the surface, the shear stress right here. It depends on the velocity gradient at the wall. So the expression for that, is given as, so again, if I draw the plate and the velocity profile at this location, say it is like this, then the shear stress at this location, let us call that as tau s, and that depends on distance. So if this direction from the leading edge of the plate is x direction, say this is y direction, then tau s is given as mu del u del y at y equals 0. So that is shear stress. So that's why this boundary layer is important, because this velocity gradient is confined to the boundary layer, and the gradient at the wall is going to determine how much this shear stress is, so how much drag this plate is going to experience. And generally we express this shear stress, which actually is a function of x. Let me write it explicitly here. So this tau s is a function of x. We write this in non-dimensional form as tau s over half rho. We take a reference velocity, which in this case is u infinity square, and this we write as, this is non-dimensional parameter cf, and this is, you can call it as local friction coefficient. This local friction coefficient, which is a measure of the shear stress on the plate. Okay. If you want to determine shear stress on the entire plate, or instead of shear stress, say I want to write drag D. This is drag on the plate. This will be given by integral tau s, which is shear stress at any location. We integrate it over the entire area. So this is over area of the plate. That will give us drag. And you can write that as integral tau s is cf times half rho u infinity square, that is tau s, times dA, integrate it over the surface, and we can non-dimensionalize it in this way. So you can write d over half rho u infinity square times area, this surface area A. This will be equal to integral, based on this equation, integral CFdA over A. And this you can call as an average friction coefficient. So we put a bar on top of that. This is an average friction coefficient, or this is also called coefficient of drag. So sometimes you write that as CD. Okay. So for a plate, this CF bar or CD just becomes integral CF. Now dA you can write as dx times the width of the plate, but the width of the plate will cancel in the numerator and denominator over L. So this is the length of the plate. So that gives the average friction coefficient, or the coefficient of drag. Okay, so that is about the velocity or hydrodynamic boundary layer, which determines how much drag the plate is going to experience. Now let us talk about the thermal boundary layer. Okay, now consider the situation that the temperature of the plate let's say it's an isothermal plate, its surface temperature is Ts. And if this temperature is greater than T infinity, so you have fluid flowing over it, it comes with a velocity u infinity and its temperature is T infinity. Okay. Now the temperature of the fluid is different from the temperature of the surface, and as soon as this fluid comes in contact with the surface, it is going to attain thermal equilibrium. So the temperature of the fluid at the surface is going to be Ts. But temperature away from the surface, temperature here is T infinity. And there is going to be heat transfer. That is heat transfer due to convection. So if at any location, say at this point, I plot the temperature profile, it will look like this. So if this represents Ts, this is T infinity, temperature profile varies like this. Okay. And at this location, let us say we have T minus, or let me write it as, say, Ts minus T over Ts minus T infinity. Let us say this becomes 0.99. Okay. So this point corresponds to the region in which this temperature gradient is confined, and this is called the thermal boundary layer thickness. This is, we indicate this as delta T. This is thermal boundary layer thickness. And the reason we take this as 99% is because this temperature here decreases not exponentially but asymptotically. So it is going to approach T infinity, okay, very gradually. But in order to define the boundary layer thickness, the thermal boundary layer thickness in which temperature gradient is confined, we take the point of 99%. So that is thermal boundary layer thickness. So starting from the leading edge, at this point, thermal boundary layer thickness is 0. And then let me draw how it grows. It goes like this. So this is thermal boundary layer thickness. Okay. And within the thermal boundary layer thickness, at the surface right here, the fluid is at rest. Okay, because of no slip condition, fluid is at rest. Because fluid is at rest here, heat transfer from the surface to the fluid. So you have, this is the direction. I'm writing this as Qs double prime. This double prime indicates flux, so I'm taking it per unit area. So this is rate of heat transfer or heat flux from the surface. At the surface right here is entirely due to conduction, because at this point, at this location, fluid is at rest because of no slip condition. Okay. Now we can use Fourier law because of that. Fourier law is applicable for conduction. And you can write this Qs double prime, this heat flux, which is a function of x. So the distance along the plate. This will be negative K, and this K is now thermal conductivity of fluid, times dt dy at y equals 0. Okay, based on Fourier's law. Okay, negative K dy, it is by conduction at the wall. And this also equals to, based on Newton's law of cooling, you can write this as H. This is the convection coefficient, and this H is a function of x. Okay, times surface temperature Ts minus T infinity. And we are interested in determining what this H is. So H based on this will be negative Kf over Ts minus T infinity times del T del Y at Y equals 0. So this is the H we want to determine. Okay. Now see, what we have here is Kf is thermal conductivity of fluid, so that is a property. But this temperature gradient you see here, del T del Y at Y equals 0. Okay. It depends on flow. It is not a property, it depends on flow. So it is going to depend on the velocity, say density of fluid, its viscosity, and other parameters, thermal parameters like specific heat. So it is going to depend on all those things. Okay. So the discussion so far is to make you understand that this temperature gradient, this is the temperature gradient in the wall at the boundary. It is very, very important. This is what is going to determine the convection coefficient. Okay. Now within the boundary layer, an important distinction is between laminar and turbulent boundary layer. Let us talk about that. Laminar versus turbulent boundary layer. So again, you take the flat plate, fluid comes with uniform velocity u infinity. It turns out that up to certain point, let us say this distance is xc. Okay. It's a critical distance. Up to this point, boundary layer is laminar. It goes like this, and the boundary layer is laminar. Okay, so what that means is fluid particles, they are actually moving nicely in layers. So this is the direction of flow and fluid particles are moving in layers. Okay. At this distance, there is transition. So there is a region in which there is transition. And the flow is sometimes laminar and sometimes turbulent, or it could be a mix. In some region it is laminar, in some region it is turbulent, and boundary layer begins to grow at a faster rate. From this point onwards, the boundary layer becomes entirely turbulent, and it grows at a faster rate. So it looks like this. So this is the hydrodynamic boundary layer thickness delta. And when boundary layer becomes turbulent, what you have is, apart from the flow which is in this direction, you have chunks of fluid particles moving randomly. So you have random, irregular, three-dimension motion of, you can say, fluid parcels, and those are also called eddies. What you have is, in this region where it is turbulent, you have fluid particles having eddy motion. So like this three-dimensional random motion. Okay, so it becomes turbulent. When it becomes turbulent, even then at the wall, because fluid velocity is 0, so turbulence is not there, and you still have a thin layer here, and this thin layer we call as viscous sublayer. So the thin layer, even in the turbulent region, that is, you can say that is laminar, or you can say viscous sublayer. Because fluid velocity is 0 there close to the wall, so the effect of turbulence is not there. Okay. Now the primary difference between laminar and turbulent situation is like this. When you have laminar flow, so let's say flow is in this direction, and if I draw a plane, then the fluid particles, or molecules, I should say molecules, not fluid particles. Actually molecules, because they have random motion, some molecules from top are coming down and molecules from below, they are going up. Okay. But fluid particles themselves, they are moving in this direction. Because of the motion of molecules, there is exchange of energy and momentum. For example, these molecules, when they move down, they are going to carry their momentum with them. and these, when they go up, they are going to carry their momentum with it and also their energy with it. So you can say that the transport of momentum and energy is due to random molecular motion. Okay, because fluid particles themselves are moving nicely in layers, but molecules have random motion and they lead to transport of momentum and energy. Okay. But when the flow is not laminar but it is turbulent flow, for a turbulent flow, let us say the main direction of flow is in this direction, and again I draw a plane. Now the parcels of fluid, those macroscopic chunks, they are moving randomly, and consider a fluid particle here. So this moves randomly, okay, across this plane. You take another particle, it moves like this. Okay. And now whatever is momentum or energy of this particle, it is transported. Okay. So the transport is now not only due to the random molecular activity but also due to this turbulence activity. So you have transport of energy and momentum also due to this turbulent activity or due to turbulence, which is going to be far more effective than molecular transport. Okay. Because you have, see, so many bunches of molecules, they move together. You have this macroscopic motion. So it is going to be much more effective. And there is going to be enhanced mixing between these layers because of this random activity. Okay. And so let me again draw the boundary layer, and in the turbulent region, so a flat plate. So boundary layer is laminar up to certain point, then there is transition and it becomes fully turbulent beyond this point. And in the turbulent region, there is region close to the wall, we call that as viscous sublayer. I already told you about this, viscous sublayer, in which turbulence does not act. So what you have is just molecular transport. And then there is a region here which is fully turbulent, and in this region the role of molecular transport is much smaller than the turbulent transport, because turbulence is so much that is mixing up the things at a much faster rate than what is possible by the molecular transport. Okay. And then there is region here next to viscous sublayer. In this region you can say both are important, the turbulence and also molecular transport. Okay, both are important. Okay. Now in terms of velocity and temperature distribution in the boundary layer for laminar and turbulent, the implication of this mixing is something like this. In the laminar region, the velocity profile is like this. So it changes gradually across the boundary layer. This is for laminar. And in turbulent, because of enhanced mixing, what happens is the gradient at the wall is very sharp. So it's very steep here, and then the remaining profile is relatively flatter. So this is relatively flatter, but you have large gradient here. The velocity profile is like this. And temperature profile is also going to be along similar lines. Okay. So you see, what you see here is del u del y at y equals 0. Okay. Del u del y at y equals 0 for laminar is much smaller than del u del y at y equals 0 for turbulent. And same is the situation with temperature. You'll have del T del y at y equals 0 for laminar, then del T del y at y equals 0 for turbulent. Okay. And the implication of this is the local convection coefficient, okay, H, which actually depends on this temperature gradient. So you'll have H laminar less than H turbulent. Okay. To be precise, if I draw how this convection coefficient H varies with distance, so I'm plotting this H, how it varies with X on a flat plate. When X is 0, see at this location the boundary layer thickness is 0. So the temperature gradient here you can say is infinite. So if temperature gradient here is infinite, then the heat transfer from the surface, the rate of heat transfer is also infinite. Okay, right here. So the convection coefficient you can say is very large. Now as X increases, the boundary layer thickness increases and the temperature gradient at the wall decreases because temperature goes from Ts to T infinity across the boundary layer. So if boundary layer is thicker, then the temperature gradient at the wall decreases, and because of that convection coefficient decreases. So it goes like this. So it's very large and then it drops. Okay. So let us say at this point this corresponds to say xc, and now the flow beyond this is in the transitional region. Okay. So it is sometimes laminar, sometimes turbulent, and convection coefficient increases. So it's like this. Okay. So beyond this point, the flow is always turbulent. It's fully turbulent. Okay. And in the turbulent boundary layer, because temperature gradient at the wall is greater, okay, so the convection coefficient is actually higher. But as the boundary thickness increases, starting from this point you see as boundary thickness increases, this temperature gradient at the wall it decreases. Okay. So the profile is like this. So the convection coefficient beyond this point again it decreases. So that is the trend. Okay. So this is the laminar boundary layer. Because boundary layer thickness increases, convection coefficient decreases. Then there is transition region, flow becomes from laminar to turbulent, and convection coefficient increases. And beyond this point, the boundary layer is fully turbulent, and convection coefficient again decreases because the boundary layer thickness is increasing. Okay. We can also define an average convection coefficient. An average convection coefficient you can write as integral h dA over A, surface area. Okay. For a flat plate, it becomes just integral h dx over L. So this will be for a flat plate. Where this h is a function of x, but this represents an average convection coefficient. So if you want to write surface flux, say qs double prime, at any location x, okay, this will be given by h times ts minus t infinity, where h depends on x. But if you want to write average surface flux, so this is average now. So this will be average convection coefficient times Ts minus T infinity. Or you want to write, say, Qs. This will be HA Ts minus T infinity. Okay. So this rate of heat transfer from the surface. So you are using the average convection coefficient times area times temperature difference. Okay. Now it turns out that the boundary layer becomes turbulent when the value of Reynolds number, okay, so this Reynolds number, I'm writing this as Reynolds number based on x. This will be rho u infinity, this free stream velocity, times x. X is distance along the plate over mu. Mu is dynamic viscosity. Okay, so if we define Reynolds number in this way, it turns out that it becomes turbulent when this Reynolds number, we are calling that as critical Reynolds number, REC, is in the range of 10 to the power 5 to 3 times 10 to the 6. So at this value of Reynolds number, okay, so this Reynolds number you see is just rho u infinity xc over mu. So boundary layer becomes turbulent at the value of xc. And this Reynolds number is in the range of 10 to the power 5 to 3 times 10 to the 6. And it depends on, okay, depends on surface roughness and also the fluctuations in the free stream, okay, depends on those things. If the value of the critical Reynolds number at which flow becomes turbulent is not given, we just take the default value as 5 times 10 to the 5. Okay, this we take as default value if it is not given. Okay. Okay. Now I want to write down the governing equations for simplicity we'll take only two-dimensional steady incompressible flow with constant properties. Okay, with constant properties. So these properties like viscosity, thermal conductivity, okay, these properties are constant. You know, in reality they depend on temperature, but we are going to consider at this point as these properties are constant. Flow is incompressible, so density is constant, and just in two-dimension steady state. Okay, so actually the flow is laminar, because when you say steady, because turbulent flow is inherently unsteady, you have that random three-dimensional motion of fluid parcels, so it is unsteady. So it's a steady. So we are talking about here laminar flow. Okay, what are the governing equations? So we'll write equation for conservation of mass, momentum and energy. So for a differential control volume, now some of these equations you are very familiar with from fluid mechanics, so I'm not going to derive those equations. Like the continuity equation, you know, the conservation of mass is del u del x plus del v del y is 0. That is conservation of mass. Then the Navier-Stokes equations, these equations you should know how to derive. I'm not going to derive right now, but you should know how to derive, and also you must remember these equations. So those equations are rho u del x plus v del u del y. So this is the inertia term in the x direction equals negative del p del x plus mu del square u over del x square plus del square u over del y square plus x. And this x is body force per unit volume in the x direction. Body force per unit volume in the x direction. So what you have is, this is inertia term ma. Okay, F equals ma, that is Navier-Stokes equation. So this term is ma per unit volume. So that is inertia term. So this term is because of pressure force, this is because of viscous force, and this is because of body force like gravity per unit volume. So that is x direction. We can write similar equation in the y direction. That will be rho u del v del x plus v del v del y equals negative del p del y plus mu del square v over del x square plus del square v over del y square plus y. And this y now is body force per unit volume in the y direction. Okay, so that is the continuity equation and the momentum equations in x and y direction. And we are taking it steady, incompressible with constant properties. So mu is a constant. Okay. Okay, now let us talk about energy equation. And energy equation, I'm going to also explain how you derive that equation. So if this is say x and y direction, we take a differential control volume and its dimensions are dx and dy in x and y directions. Okay. And the conservation of energy will be, you have energy coming into the system and energy going out of the system. Okay, so let us write what those terms are. You have energy coming into the system, say from the left face, because of advection, because of flow. Okay, and that energy will be the density rho times velocity in x direction u times dy. This indicates mass flow rate. Okay. Mass flow rate through this phase, rho u dy. Mass flow rate times specific heat, Cp times temperature, T. Okay. So this term represents enthalpy, the rate at which enthalpy is going into the control volume. And you remember from fluid mechanics and thermodynamics, when we say enthalpy, we have included the internal energy and also the work done by the pressure forces. Okay, because enthalpy is U plus PV, where U is internal energy and PV represents the work done by the pressure forces. So this is enthalpy that is advected into the control volume. We are going to neglect kinetic energy because it turns out that in heat transfer problems, a lot of time the effect of kinetic energy in the energy equation is negligible in comparison to this internal energy or enthalpy term. Okay. So we are not going to consider kinetic energy. Okay. Okay. So this is energy that comes in, and also potential energy, gravitational potential energy, its effect is negligible. Energy that is convected out of the right phase, we can write this as, say, this term, which will be rho u cp t dy plus, based on Taylor series, del by del y. No, sorry, it will be del by del x. This distance, this is x direction, this is dx. So it will be del by del x of rho u cp t dy. So this is enthalpy that is advected from this phase, and this is enthalpy that comes out from the right phase. Okay. Similarly, we can write terms in this direction. Let me write those also. So from the bottom phase, enthalpy that goes in will be density times velocity times dx. Okay, this is mass flow rate times cpt. And from the top phase, if I write, say, this term as, let me use some shorthand here. Let me just call this as, say, qy. Okay. So what comes out from here will be qy plus del by del y of qy times dy. Let me see. In this equation also, actually, you have dx also here. I had forgotten to written that. Okay, that comes out. So that is enthalpy that is advected. Okay. Now, apart from this, you have also conduction. So let me show those terms here. From the left face, because of temperature gradient, you have conduction. That will be given as negative K times this area. This area is dy times temperature gradient, del T del X. That is convection. That is conduction. So we wrote advection, and this is conduction. Okay, what comes out from the right face will be negative K dy del T del X plus, it will be del over del X of negative K del T del X times dx dy. Okay, this is conduction from the left face and from the right face. And similarly, you can write down conduction from the bottom. Okay, this term will be negative K dx times del T del y. And you can write conduction from the top. Okay. So we considered advection, conduction, and we are saying it is steady state. So there is no change in energy of the system as such. So whatever energy goes in, that energy comes out. We are neglecting kinetic energy and potential energy. Now, apart from these terms, there is also work done by the viscous forces on the control volume. Let us look at that also. Also work done by the viscous forces. Okay. So you have, so this is the control volume. And when I say viscous forces, I am not including pressure in that, because work done by pressure, we already included in this term here. This is enthalpy. This includes internal energy and also work done by the pressure forces. So when you say viscous forces, it does not include pressure. Okay. And viscous forces, they are given like this. So on this face, if say viscous stress is say tau xx in this direction, it is going to be in this direction on the right face, and say the shear stress on this surface we show like this. You have this understanding based on fluid mechanics also. So this will be shear stress on the plane that is perpendicular to x direction. So I'm writing that as tau x, and it is in the y direction. So tau xy. Okay. On the right side, it will be in this direction. And then at the bottom, you have, let's say this is tau yy. At the top face, it will be in this direction. And you also have this shear stress at this surface. This will be same as tau xy. Okay, it is tau yx, but they have same magnitude. So this is tau xy. And at the top face, you have in this direction. Okay, so those are the viscous forces on the control volume, and there is work done by these viscous forces on the control volume. So we have to consider that also in the energy equation. Okay. Now, first let me write down the expressions for these. And you know these from fluid mechanics, you must remember tau xx is given as twice mu del u del x. Tau xy is mu del u del y plus del v del x. Okay, that is tau xy. And tau yy is 2 mu del v del y. So those are expressions for these viscous stresses. Okay. Now let us write down the work done by these. See, at the left face, this is tau xx, and the fluid velocity here is u. We are taking u positive in this direction. Okay. So the work done by this force, by this stress, will be tau xx times area. This area is dy. We are taking unity length in the vertical direction because this is a force. Multiply this with velocity. Velocity is u. But they are in the opposite direction, so a negative sign. Force is acting in the this direction, and velocity at this point, that is in the this direction. Okay. So this is work done by this force. Okay. Let me call this as, say, I'm just using shorthand, this rate of work done. Let us just call this as W1. Okay. Now the rate of work done by the force at the right face will be W1 plus, see, let me explain it more clearly. So the shear stress, sorry, this viscous stress here, and analogous to tau xx at this face, will be tau xx plus del x of tau xx times dx. And velocity here, if velocity here was u, velocity at this point is going to be, if it was u here, it will be u plus del u del x times dx. This is the velocity here. But now you see, the force is in this direction and velocity is also in this direction. So work done by this force is positive, and it is going to be a product of these. Okay. And we can neglect the higher order term, which will be a product of these two. If you neglect that term, so what you will have from the right face will be tau xx u plus, it will be u del by del x of tau xx times dx plus tau xx times del u del x dx, and then multiply this with the area dy. Sorry, dy. Okay, so this is work done by the force you have on the right face. Okay, so the total work done by these two, the total of these two, you see one term will cancel because it is negative here and it is positive here. So you'll get, it will be this del x of tau xx u times dx dy. Okay, this is work done by that. Okay, so similarly we can add to this work done by all the other forces here. So we consider this and this. Okay, similarly you consider, okay, these and also the shear stresses that are acting on this. Okay, so let me write the total expression. So what you will get is this term plus you will get del y of tau yy v times dx dy. Okay, plus because of shear stresses you will have del x of tau xy v tau xy v times dx dy plus there will be del y of tau xy u times dx dy. Okay. So this is the work done by the viscous forces on the control volume. Okay, work done by the viscous forces. We can expand this because I gave you already expressions for tau xx, tau yy and these. So you can substitute those and expand this, write it in a different form. Okay. So now the energy equation becomes, when you do the energy balance, there is advection, diffusion and work done by all these viscous forces. Okay. So your energy equation will become, when you do the balance, I'm just writing the final thing, it will be rho Cp u times del t del x plus v del t del y equals k del square t over del x square plus del square t over del y square plus a term phi, and this term is due to viscous work. This is called viscous dissipation. Okay, this term is called viscous dissipation. Okay, so that is the energy equation we get. So this corresponds to net advection. You have advection, flow into and out of the control volume. This term corresponds to advection. This corresponds to net conduction, and this is viscous dissipation. Okay. It turns out that for low speed flow, okay, so you say like say Mach number is less than 0.3, so the flow is incompressible. The effect of this viscous dissipation is negligible. Okay, so we are not even going to consider this term in our analysis. We have this term in the energy equation, but its effect is negligible for low speed flow. So we'll just have a balance of these two terms. Okay, so those are the equations we got. Okay. Now, see, our interest is in the determination of convection coefficient. So let us talk about what methods do we have. So how to determine H for various situations. See, one option is we use CFD, okay, computational fluid dynamics. So we solve the governing equations, so the equations we just derived, so solve those equations using computer, and you are going to get all these things, okay, how velocity, say density, temperature, all these things, how they vary with X, Y, and Z. Okay. And based on this, you can determine convection coefficient. Not only convection coefficient, in this case you have all the details of the flow. Okay. So that is one option, but it is just CFD analysis is just going to give us some numbers, not physical understanding as such. So it is there for solving complex problems, but we need some physical understanding also. So there are other methods. Another option is we use dimensional analysis. But whenever we use dimensional analysis, we have to also do experiment. We can use dimensional analysis along with experiment to determine this convection coefficient. Okay, let me explain. For example, say the problem is we have a cylinder. Let's say its diameter is D, and then there is flow over the cylinder. This is U infinity. And if the surface temperature of the cylinder is different from the fluid temperature T infinity, okay, there is heat transfer between the cylinder and the fluid, and we want to determine the average convection coefficient. Okay, this is average convection coefficient, because H is actually going to vary. The local convection coefficient is going to vary from point to point, but we can define an average over the cylinder. Okay, we want to do that. When we talk about dimensional analysis, generally we write like this. So this H, this convection coefficient, it is a function of some parameters, and we have to be very careful when choosing these parameters. Let me write down the parameters which are important. There is density, the velocity of the fluid U infinity, some length scale, we take that as the diameter of the cylinder, its viscosity mu, thermal conductivity of the fluid, that will be important, because it is by conduction, heat transfer is by conduction at the wall. That will be important, and the specific heat of the fluid. Okay, Cp. These are going to be important parameters. Okay. Now, we have to be very careful when we are writing like this, because accidentally, if you miss some of these important parameters, then the analysis is going to be wrong. And if you include more parameters, then you are making it unnecessarily complicated. Okay, so that's the thing here. And you remember from fluid mechanics, we have the Buckingham pi theorem. We can use that to non-dimensionalize, okay, these. So in this case, you see we have 1, 2, 3, 4, 5, 6, 7. There are 7 parameters. And we also see how many physical dimensions we have to describe these parameters. Actually, we are going to have 4 dimensions here. There will be length, time, mass, and also temperature. So you have 4 physical dimensions that describe these parameters. So the number of pi terms, based on Buckingham pi theorem, will be 7 minus 4. There will be 3 pi terms, or 3 non-dimensional parameters. Okay. So we can determine those 3 non-dimensional parameters, and when you do that, you end up with these parameters. You get rho u infinity d over mu. This is one parameter, and this we call Reynolds number. Another non-dimensional number you get is h bar d over kf, and this we call Nusselt number. We use symbol Nu for this Nusselt number. And the third you get is mu Cp over k. This is the third parameter you get. But this parameter we can write in a different way. You can write this as mu over rho times rho Cp over k. Mu over rho is nu. Okay, this nu is kinematic viscosity. Okay, sometimes we also call it momentum diffusivity. It is nu over k over rho Cp. This is thermal diffusivity alpha. So mu over alpha. And this parameter is called Prandtl number. And we use symbol PR for this. Okay. So you see, by doing a dimensional analysis, we ended up with 3 parameters: Reynolds number, Nusselt number, and Prandtl number. And we can write Nusselt number is a function of Reynolds number and Prandtl number, because these are the 3 parameters. And this Nusselt number, this characterizes convection coefficient, because this is Hd over k. So this has convection coefficient in it. Okay. So now what we can do is, theoretically, by dimensional analysis, we got this insight. We can do experiments for different values of Reynolds number and Prandtl number, and experimentally determine what this correlation is. Okay, so you get the correlation from experiments. But now see, the advantage is we have to vary only 2 parameters, Reynolds number and Prandtl number, whereas originally to begin with we had 7 parameters. Okay, so get this correlation from experiment, and the correlation we get is going to be applicable for geometrically similar systems. So it will be applicable even for a smaller cylinder or a larger cylinder if the experiments were for a cylinder. If they are for an aerofoil, let us say, then they are going to be applicable for aerofoils which are geometrically similar. So that's the advantage of this dimensional analysis. So that is one method we have. So we talked about we can use CFD and solve for the whole solve for the governing equation, and we get the convection coefficient from that. Or we can do this dimensional analysis along with experiments to get the convection coefficient. Okay. Now, third way is, now this is theoretical, and I'm going to talk about this in some detail so that you get insights into the equations we have. Actually, it turns out that the Navier-Stokes equations, okay, those equations, you know, those cannot be solved, okay, except by using computers for external flow. So external flow means we have flow over an object, like we have flow over a plate or we have flow over a cylinder. So that is external flow. And Navier-Stokes equations, we have Navier-Stokes equations, and along with that there is energy equation. Those equations cannot even be solved for external flow. Okay. For internal flow, you know, if the flow is laminar, we have several solutions. There is Coet flow, okay, Poiseuille flow, there are some other solutions. But for external flow, there is no solution. So what we do is, from Navier-Stokes equations, first we derive the boundary layer equations. We'll talk about that. Okay, derive boundary layer equations. And the boundary layer equations, okay, these equations can be solved, although it is mathematically involved. But these equations can be solved for laminar flow. Okay, for simple geometries, like for example, for a flat plate or for an aerofoil, and even for a cylinder, okay, those equations have been solved. So what I'm going to explain is, starting from the Navier-Stokes equations and the energy equation, first we will get the boundary layer equations, and then we are going to solve those equations for a particular case. Okay. But remember that this is going to be applicable only for laminar flow. Okay. Now consider that the external flow over an object. So there is an object here and there is external flow over it. So fluid comes with velocity here u infinity, and it flows over this surface. Okay, this surface could be like this. Okay, so like this. And if we indicate x direction along this, so it need not be straight. Okay, x direction is along this, and y direction is perpendicular to this. So at any location, let's say at this location, okay, y is perpendicular to this. That is y. Okay. The boundary layer is going to develop over it. So let's say this indicates, okay, how delta, this is hydrodynamic boundary layer, how it develops over this surface. And similarly, okay, you have the thermal boundary layer also. Okay. Now let me write down the governing equations once again. We have del u del x plus del v del y. Okay, this term is zero, that is continuity. there is momentum equation in x direction, that is u del x plus v del u del y, and there is density here. I'm taking density on the right hand side. This will be negative 1 over rho del p del x plus, this becomes kinematic viscosity, and here you have del square u over del x square plus del square u over del y square. Okay, similarly, equation for the momentum in the y direction, that will be u del v del x plus v del y equals negative 1 over rho del p del x, sorry, del p del y plus mu, this is nu, this is not mu, del square v over del x square plus del square v over del y square. And the energy equation, we got was u del t del x plus v del t del y equals, here you will have thermal conductivity over rho Cp, so that becomes alpha del square t over del x square plus del square t over del y square. Okay, so those are the equations, and I have neglected here, okay, the body forces x and y, and also viscous dissipation phi, because for low speed flow viscous dissipation effect is negligible. And if it is forced convection means there are external means of inducing this flow, so that is forced convection. For forced convection problems, the effect of body forces, the only body force mostly you are going to have is gravity. The effect of body forces is negligible. Okay, so I have neglected these terms. So these are the equations. The essence of boundary layer approximation is, when we say boundary layer approximation, see, from this point to this point, okay, across the boundary layer, flow velocity changes from 0 to u infinity. It changes from 0 to u infinity. So there is large gradient in velocity in this direction. Okay, similarly, there is going to be large gradient in temperature in this direction. If temperature here is Ts, temperature here is T infinity, then temperature gradient in this direction is large. Whereas temperature gradient in this direction is going to be very small in comparison to that. Velocity gradient in this direction is going to be very small. Okay, so the essence of boundary layer approximation is, I'm just giving you some examples here. Okay, del u del x is much smaller than del u del y. Okay, so velocity gradient in the y direction is very large in comparison to x direction. Okay. Similarly, you have del t del x is much smaller than del t del y. Okay. So in reality, what we do is, on these equations, we do an order of magnitude analysis. I'm not going to do that, but I just gave you a simple understanding that some gradients are negligible, and similar to that, actually, you will also have del square t over del x square is going to be much smaller than del square t over del y square within the boundary layer. Okay. Now what happens is, because of these, when we introduce those in these equations, in the y momentum equation, it turns out that actually these terms drop out when we do an order of magnitude analysis. All these terms drop out, and the equation becomes del p del y is 0. Okay, that's the only term that remains. So you get del p del y is 0. Okay, this means actually that pressure is a function of x only. So pressure does not depend on y. So you can write del p del x as dp dx as total derivative, or you can write this as dp infinity dx, where p infinity is pressure away from the boundary layer. So in this plot, if you, in this figure, if I want to indicate P infinity is pressure. It varies in the x direction. P infinity varies in the x direction, but this is away from the boundary layer. So what we got is del P del y is 0 and del P del x is dP infinity dx. So what that means is, if you take this point and this point, they have same pressure. Pressure variation in y direction in the boundary layer is negligible. Okay, and pressure variation in the x direction dp dx, that can be written as dp infinity dx, how p infinity changes with x. So that is what the y momentum equation gives us. Okay. In the x momentum equation, this term is very small in comparison to this term, so this term goes. Okay. And similarly in the energy equation, this is very small in comparison to this, so this term goes. So what we have is now the equations that remain. See this equation here, except this term, and the energy equation here, and we have the continuity equation. This remains unchanged. These equations are called boundary layer equations. Okay. And these equations can be solved, whereas Navier-Stokes equation, that cannot be solved. These equations can be solved without using computer. Okay. And mathematically, the reason for that is, I'm not going to explain too much about that, but Navier-Stokes equations, those equations are elliptic partial differential equations. Okay. And when we have an elliptic equation, so our problem was this. Okay, let's say flow over this. When you have an elliptic equation, then solution at any point in the domain is influenced by solution at any other point in the domain. Okay. So this point is influenced by this and also this. And that is why we have to solve over the entire domain simultaneously. Whereas if the equation is parabolic, so the boundary layer equations we got, okay, those equations are parabolic. For parabolic equations, solution at this point depends only on solution in this region, upstream region. It does not depend on downstream. Okay, so that's the advantage. And because of that, we can march. We can start from this and we can march in this direction, because solution here is not going to influence solution here. So we can march, and those equations can be solved for some cases even without using computer. Okay, so they have been solved. Those are boundary layer equations. Now, in the x momentum equation, we have this term that is del p del x, which actually becomes dp infinity dx, because pressure varies only in the x direction. Okay. So the first step when we solve the boundary layer equations, the first step is to get this dp infinity dx. And let me explain you briefly how that is done. Okay. Now, because boundary layer is thin, boundary layer grows like this. In the region outside the boundary layer, so in this region, flow is inviscid and irrotational. It is inviscid and irrotational flow. And because of that, we can define a potential function. Okay, phi is potential function. And we can solve for phi. Okay, so we don't have to consider viscosity. We discussed this in detail in fluid mechanics. But potential function is applicable for inviscid irrotational flow. We can define the potential function and solve for this. Okay. And then we can solve for velocity from phi. So, in 2-dimension, like u is del phi del x, v is del phi del y. Okay. So once we get potential function, we have the velocity. Okay. And then if the flow is irrotational, that Bernoulli's equation is applicable. If the flow is irrotational, it is applicable at any 2 points. So you take this point and this point, Bernoulli equation is applicable because in this region there is no influence of viscosity. Okay. Effect of viscosity is confined to the boundary layer. So the Bernoulli's equation is valid, and that equation will be, if I write like this, say P infinity plus half rho u infinity, and P infinity is a function of x and u infinity also is a function of x. So this is a constant. Okay, that is Bernoulli's equation, and we can differentiate this. So you get dp infinity over dx equals negative rho u infinity du infinity over dx, and this you get based on this. Because the idea is we are able to get this pressure distribution, okay, this dp infinity dx by using the velocity potential and then by using the Bernoulli equation. And this dp infinity dx, actually this term depends on the shape of the object. It depends on the shape of the object. And we can solve for this beforehand. Okay. So now let us look at the boundary layer equations again. Okay, so this is the equation we have to solve, the Navier-Stokes equation, and this is the energy equation. But this term here, this del p del x, which is same as dp infinity dx because of boundary layer approximation, we have that term beforehand based on what I explained you, based on the potential function, and by using Bernoulli's equation, we have this term beforehand. Okay. And for a flat plate, for flow over a flat plate, this term is 0. This dp infinity dx. Okay, there is no pressure gradient in the x direction. Okay. So the general idea in these equations will be, see, first these two equations can be solved. Okay. And by solving these two equations, you will get u and v. Okay. We get u and v, pressure is already known. We get u and v, and then after getting u and v, okay, solve this equation because this equation requires u and v. So we have u and v, solve this equation, energy equation, it will give us temperature. and once we have temperature, we can determine the convection coefficient. So that is the general idea. Okay, and these equations can be solved even without using computers. We are going to talk about a special case, that is for a flat plate. We are going to solve these boundary layer equations, and actually this solution is called Blasius solution. And Blasius was a student of Prandtl. You know, the boundary layer theory was given by Prandtl, and Blasius was his student, and he actually solved this. So first let me write down the boundary layer equations for flow over a flat plate. We are considering a flat plate. So the equations are the continuity equation, del u del x plus del v del y, that is 0. X momentum equation, that is u del x plus v del u del y equals nu del square u over del y square. And we have taken here dp dx is 0 because it's a flat plate. And energy equation, u del t del x plus v del t del y equals alpha del square t over del y square. So these are the equations. Okay. Now, okay, just to keep you on track, what I am discussing is how can we get convection coefficient. Okay, because that is what we want. One method is we just solve the equations with full complexity by using CFD. That's a numerical method. Other is we do dimensional analysis. We did that, and you found that Nusselt number is a function of Reynolds number and Prandtl number. And then we can do some experiments to get that correlation. So we have convection coefficient. That is another method. Okay, third is we want to solve the equations we have theoretically. But the problem is Navier-Stokes equations cannot be solved for an external flow without using computers. But we modify those equations with boundary layer approximations, and we get boundary layer equations, and those equations can be solved. And we are solving those equations for flow over a flat plate. And again, our objective is for this particular situation, it is a laminar flow. We are interested in determining what is convection coefficient, and what we are discussing is it should give us that. Okay, so that is the objective. Okay. So now the approach of Blasius was, so if this is the boundary layer, this is hydrodynamic boundary layer delta, and within the boundary layer velocity profile, you know, it varies like this. Velocity is 0 here in x direction, and it varies from 0 to u infinity. Okay, actually we take this point as 0.99. So see, let me write here. So u is actually 0.99 u infinity at the boundary layer thickness at delta. It is not u infinity, it is 0.99 u infinity. So this is the profile. Okay, if you take at any other location, you have similarity in the sense it is 0 here, and when y becomes delta, okay, it becomes like this, almost u infinity. Okay, so based on this, you can say that at any point within the boundary layer, so at any location x, you can write u over u infinity. U infinity is the velocity outside the boundary layer. And this does not depend on x in this case, because there is no pressure gradient in the x direction. Okay, so this is just a constant. U over u infinity is going to be a function of y over delta. because u over u infinity is 0 when y over delta is 0, and this becomes 1 when y over delta is 1. Okay, so if you argue that in between also these profiles are similar, then you have this sort of situation. Okay, we can do an order of magnitude analysis on this equation. Let me do that. That gives us some information about delta. So I'm writing that equation again. U del u del x plus v del u del y equals nu del square u over del y square. Now in the analysis within the boundary layer, see, u is of the order of u, and del u del x, see, at this point, okay, velocity is u infinity, and then see it is u infinity, you can say here, and along this at any distance x, okay, velocity is very small, so this change in velocity is actually u infinity. So you can argue that del u del x is of the order of u infinity over x. Okay, so this term is of this order. I'm not writing for this term. Let us look at this one. The order of this term will be, see, this is nu del square u over del y square. This will be in the y direction. Velocity is 0 here, and it becomes u infinity as y becomes delta. So this term is of the order of u infinity over delta square. Okay. Del square u over del y square is of the order of u infinity over delta square. And based on this, you can write that delta has some relation in this form. It is because they have same order. It will be nu x over u infinity. Okay. So when we define that u over u infinity, this is a function of y over delta. Okay. And let us write this y over delta as eta. This eta is y, and delta is of this form. It is related to this expression nu x over u infinity. So this gives us eta is of this form, y times square root u infinity over nu x. Okay, eta is of this form. So u over u infinity is a function of eta. And now Blasius defined a stream function psi, and there is a reason why it is defined in this way, but I'm skipping some of the details here. If we define a stream function like this, u infinity square root nu x over u infinity times a function of eta. If a stream function is defined like this, where you know we have u is del psi by del y, and v is negative del psi by del x. Okay, that is for a stream function. Then the continuity equation is automatically satisfied because we have this stream function. Okay, and we have to only look at the momentum equation in the x direction. Okay. And I'm just going to give some idea here. For example, this u, that is del psi del y, we can write this as del psi del eta times del eta del y. Okay. Because you see psi is not a function of y explicitly. You don't have any y here. You have eta, but eta is a function of y. So we are applying chain rule. So u is del psi by del y, which is del psi by del eta times del eta by del y. And when you do this, you get u is u infinity times df d eta, or we generally write that as u infinity times f prime. So this f prime means f has been differentiated once, and see, this is not partial derivative, this is total derivative. F is just a function of eta, so this is df d eta. You get u equals this. Similarly, we can write expressions for v, okay, del u del x and del u del y. We can write expressions for these and substitute those expressions in the momentum equation, in this equation. Okay, so after substituting, you get an equation. I'm just going to write that down. So that equation is actually an ordinary differential equation. You get 2f triple prime. That means f has been differentiated 3 times with respect to eta, plus f prime equals 0. You get this equation. So this is actually the momentum equation. So momentum equation, the original momentum equation, which was a partial differential equation, now becomes an ordinary differential equation. Okay, because of using that similarity, that within the boundary layer velocity profiles are similar. So you can write u over u infinity is a function of y over delta or a function of eta. So based on that we get this. Okay. So it's a third order non-linear differential equation. You need 3 boundary conditions to solve this, and those 3 boundary conditions are, let us first write in terms of u and v. You have u at any x when y is 0, so that represents val is 0. Similarly, v at any x at the val is 0, and u at any x when y approaches infinity, so this is outside the boundary layer, this will be u infinity. So those are the 3 boundary conditions in terms of u and v, and we can write these boundary conditions in terms of f. I'm skipping the details here, but you get f prime 0 is 0, okay, f 0 is 0, and f prime as eta approaches infinity, this is 1. Okay, so these 3 boundary conditions in terms of u and v, those are same as these boundary conditions in terms of f. Okay. So this equation, there is no analytical solution for this equation, but this ordinary differential equation, it can be solved numerically very easily, even without using computer. Okay, so Blasius, he actually solved this equation. Okay, and what you get is, after solving this equation, you get the velocity profile. And I am plotting after solving this equation. So what you get is, you get f as a function of eta, or you get f prime as a function of eta. You get this. Okay, that is the solution. When you solve that equation numerically, okay, you get this. Okay, now I'm just plotting this solution here. So when you plot it, if I have, say, eta here, and eta goes from 0, it is increasing in this direction, and on x-axis, if I'm plotting f prime, and if you remember, f prime was u over u infinity. Okay. So we are plotting f prime versus eta. We got that by the solution of that equation numerically. When eta is 0, f prime is 0, and then it increases, the profile is like this. and when eta is 5, the value of f prime here is 0.99. Okay, it is 0.99. Okay, so see, when eta is 5, okay, when eta is 5, u over u infinity, that is f prime, is 0.99. So u is 0.99 u infinity. That means this value of eta equals 5. That corresponds to delta, because this is how delta is defined. Boundary layer thickness is defined as the distance at which velocity becomes 99% of free stream velocity. So this corresponds to the boundary layer thickness delta. Okay, and this eta was actually delta times square root u infinity over mu x. Okay, so this was the, this was y, sorry, it was y, but instead of y I have written delta, and at that point this eta is 5. Okay, so this was y, but when y equals delta, eta is 5. We got that from the solution here. Okay, when eta is 5, then y corresponds to delta, because velocity is 99% of free stream velocity. And based on this, you can write this delta equals, just rearrange this term, and you get delta is 5x over square root of Reynolds number x. Okay, this is very important relation. So this is for laminar flow over a flat plate, and it tells us how boundary layer thickness changes with x. So you have x here, and in the Reynolds number you have square root of x. So actually you'll get delta is proportional to x to the power half. Okay, so this is how boundary layer thickness changes, and we also got an expression for the boundary layer thickness. Okay. Now the shear stress at the surface tau s, that is defined as mu del u del y at y equals 0. Okay. But we have this velocity profile available from the solution, and we can differentiate that and take the value at y equals 0, and we get an expression for tau s also. Okay. Instead of tau s, I'm writing the expression you get by tau s, divide this with half rho u infinity square, okay, which is actually the local friction coefficient Cf based on Blasius solution, because you already have this thing available, so you just have to substitute that. It turns out to be 0.664 over square root of Reynolds number x. Again, a very important relation, okay, which is very valuable from fluid mechanics point of view. So it tells us how the local friction coefficient, it varies with x. Okay, how it varies with x. So you see the dependence is Cf varies with x to the negative half, because you have x here in the denominator, it becomes negative half when you take it above. Okay, so those are the solutions. So up to this point, we only solved the momentum equation by using the method of Blasius, and the result is we got the velocity profile. And from the velocity profile, you have the boundary layer thickness delta, and you also get the shear stress tau s. Okay. So in the next class, we are going to continue, and we are going to now solve the energy equation. And from solving the energy equation, we will get the temperature profile, and once we have that, we can write an expression for convection coefficient, because convection coefficient is related to temperature gradient at the surface. So we'll get convection coefficient that we are looking for. We'll stop at this point.